All right, good morning. So, like this year, everyone has the feeling like this is a weird year. Like, uh, I saw like, next month I was supposed to be somewhere in Japan, maybe in Tokyo. I should be visiting those arenas, fields, courts, whatever you call them, built for Olympics. But turns out that there's no Olympics this year, which is supposed to be in August this year, and turns out that there's no way that I can visit Japan right now unless I'm willing to take a 14-day quarantine in a hotel in Japan and then fly back. So so this is a weird year, but I saw some of you put some interesting video in the chat message before the class. So sounds like at least you guys have a very refreshing Thanksgiving holiday. That's a good thing to know. And because you are refreshed, I know you are now fully recharged to interface with the challenges that we will give you by the end of the quarter. So, but before we start the new topics, it's always good to talk about where we are coming from. So first of all, we talk about all processors right now. They are having some sort of pipeline design. And theoretically, we should be able to, smoothly output an instruction for each cycle for a pipeline processor. However, it's so hard to achieve that because we have three different types of hazards. Structural hazard, meaning that the hardware is not allowing two instructions access the same unit concurrently. And control hazard, meaning that we always have an issue. We have an issue of determining who is the next instruction to fetch. And data hazards, meaning that we have problem getting the input that we need for execution. And we have been talking about the solution to address the first two. And then in the last lecture, we were talking about a better way to address data hazard, which is dynamic out-of-order execution. And the basic idea of dynamic out-of-order execution is that for an instruction, if you want to execute it, all you need is that, well, first of all, you know what's that instruction, meaning that the instruction is decoded, and whatever inputs that you need are ready, meaning that we don't depend on anything anymore, and you have a functional unit that is available for you to use. So all it says that if you want to execute an instruction, there are three things that you have to check. The instruction has completed its own work right now. No other instruction is occupying the next stage, and the next stage has all its input ready. So to support that kind of idea, out-of-order execution, we have Tomasuo algorithm first, and the Tomasuo algorithm because it attach reservation stations for each functional unit. So so if you don't have you don't have sufficient reservation station for a popular set of instructions, then turns out that you will have a structural hazard again in a reservation station, which bottlenecks your execution. So another way which you read in a paper called register renaming is now more popular. So the paper you read is MIPS R10K and Alpha 21264, and they were popular process. Well, they were pretty famous processor at their era, and even though for x86 processors, we all use register renaming. So the basic idea of register renaming is that instead of putting reservation stations associated with each functional unit, they are now putting it in a central place called physical registers. And you have a register mapping table, try to remap the architectural registers like your X1 to X31 to physical registers that usually, like right now, microprocessors has 64 to 128 physical registers that provide a temporary storage for those values. And then you have a renaming logic. Try to rewrite your instructions, but instead of using the architectural registers, you are going to use the physical registers to specify their inputs and outputs. And so that's the idea of register renaming. And after you rename the instructions, they will be put into instruction queue for execution. So that's the basic idea of register renaming. So with register renaming, you will see that for the same sequence of instruction now, we don't have the issue of fighting for reservation stations. However, even though for register renaming hardware, you can see that, well, we have 10 instructions, we still have to spend 12 cycles to issue all of them. Plus, if you look at the pipeline that we have, right, we have a address resolution plus the load store queue for memory. We have the integer ALU, we have the floating point adder, floating point multiplier, we have the branch. But because we fetch one instruction at a time, so we can only schedule one instruction at a time in most of the case. So another idea called superscalar, meaning that, okay, we widen our instruction fetch, instruction decode, register renaming logic, issue stage, to allow more instructions to be decoded, fetched, renamed, and issued at the same time. So if I have a processor with fetch width equal to 4, issue width equal to 4, then theoretically, if these 4 instructions, they belong to different types of pipeline in execution, I can put 4 instructions into execution at most. So that's the basic idea of superscalar. So with superscalar processor, we are supposed to get better performance. But what we end up with is that if the software programmer is careless, or say if the software programmer doesn't know how to write code that can exploit better, well, if you have a code like this, right, then turns out that even though you have superscalar processor, it still takes 13 cycles to issue this 9 instructions. So it's really important that a software programmer knows how to efficiently use your pipeline. And the other thing is that, well, for the given pipeline right now, there are 2 other issues. First of all, because we have auto-over execution. So if instruction 6, which is a branch here, if it's mispredicted, and at this point, you see instruction 8 is already done, right? So how can we revert that instruction that has been done, right? One more thing is that we also have a lot of wasted slots because the low instruction level parallelism from these pieces of the code. So today's lecture, we are going to talk about how to address this. So so here's our current standing of each team. And today we are going to talk about the concept of speculative execution and ReorderBuffer. We are going to talk about simultaneous multi-threading and the chip multiprocessor. So we say that we have issues with branches misprediction. However, just want you to refresh your mind, including branch. In what pipeline stage, how many of the following pipeline stages can we potentially change the PC? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. time is up. Okay, so now it looks like we really need some kind of discussion. So why don't we spend about 2 minutes to have the discussion? Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's pick a group to let us know what do you guys think, because right now it seems like C is a more popular answer. Okay, Valor. Who is the scriber? Okay, Daniel.
Hi, I think we mostly concluded that it was 3.
What are the 3 and why they could potentially change the PC?
So we were thinking that I guess we can start with instruction fetch. If it's fetched from somewhere, I guess, since the instructions are fetched from memory, you could have like TLB misses or other such things where that would generate exceptions.
So TLB misses, would that generate exceptions?
Well, perhaps
so
not. You just have to. It would cause stalls, but
yeah. So will it change the program counter?
No, I guess not.
So what would change the program counter?
You could have for branch instructions, the execute stage would, and then for.
So this is branch.
Let's see. You could have. I guess I don't know if the processor has no way of knowing whether memory, I guess, is illegal to access. So in the memory
Well,
state,
it knows illegal access, right? If what? You learned this before, and it sounds like
there could be valid.
it's the only lecture that I don't have. It's the recorded lecture, right?
Oh, the recorded one.
Sounds like you didn't watch it.
No, I did. There could be like they have different extra bits in memory, like the valid bit or dirty bit or something like that.
Right. So if you are accessing a protected page, right, then it will have illegal access. And what is that? So that's something like, right.
Well,
So you will have to trigger an exception handler to handle that, right?
Yeah.
And that exception handler is part of your operating system kernel code. So you will have to change your PC. And the same thing, which you are almost close, is that the TLB misses won't trigger an exception. But if you have a page fault,
page fault.
Meaning that I cannot find a translation between the virtual and physical address, not even in the page table, right? Because the page is not allocated yet, right? Then it will trigger the operating system kernel code to get involved. And the operating system kernel code is not part of your program. So you will have to jump your PC to the operating system kernel.
Okay. So in that case, it would be 1, 3, and 4.
1, 3, and 4, right? But that's not the only, right? So first of all, right, if you have page fault illegal address, you will need the operating system page fault handler and illegal like permission check or whatever handler to handle that. So you will change the PC. Well, so for instruction decode, a lot of people might not think about this as like if I have an unknown instruction, right? Then it will also be a handler that we need to deal with, right? And the execution stage, right? There are a lot of things that could happen. So for example, not just branch misprediction, there could be overflow, underflow divided by 0. Those are exceptions that would need a spatial handler in the operating system to handle. And as long as you need a handler, exception handler, the handler itself is just software and it's code. So your program counter will change. And again, for data memory access, you need to handle page fault, you need to handle illegal address if they occurs. So actually 4 of the pipeline stages, they would change the PC. So in fact, anything, almost everything during your execution would potentially change the PC, right? So some of you were asking about like unknown instructions. So sometimes your compiler might generate an instruction that is not compatible with the current architecture. So for example, if you have an instruction that, if you have a binary that is compiled with saying like AVX 512, and if you try to run it on the TI-05 machine, that's definitely not allowed because that instruction, they don't know who is that, right? So that's an unknown instruction. So so that's why unknown instruction it occurs, right? So and in your homework in your project, you probably will see that, well, and a lot of instructions like new generations of the Intel processor, they support it, but not in a generation of the processor that I'm working on. So if you use the same binary that compiled on the newer generation of the Intel processor and try to run it on the elder generation of the Intel processor, it won't work because well, first of all, it will work a little bit, and at some point it will generate the unknown instruction exception. So that's why this is something that we have to deal with, and the instruction set architecture evolves. So there's no guarantee that you will always receive a binary that contains instructions that every instruction you can execute. And if you don't know what are the exception handlers and why it's changing the PC, well, I cannot tell you too much about this because this is architecture class right now. And if you really want to know more, you should take my CS202 next quarter. So far, I have only 16 enrolled. So it would be great that if some of you can participate in a class next quarter, and it's in a pretty good time. It's a dinner time, and it works out for everywhere on Earth. That's what I would say. Like it's 6:30 p.m. On the West Coast, so technically 9:30 p.m. on the East Coast, or in Asia, it's also 10:30 a.m. in the morning, which is the perfect time. And in India, I believe it's also like something like 6:30 a.m. So if you wake up early, it will work out, right? So it has a pretty good timing. It's a bad timing if we have to meet in person, but virtually it's a good timing. You can consider that you are watching on YouTube during your dinner time or whatever time, right? And if I get more of you, I can enjoy a full TA. So that's probably the main point why I need more of you to be in the class. All right. So okay. So that's so every well. So back to this question. So if you look at the pipeline, everywhere during the execution, except for the last stage called write back, could potentially change your PCs. So if you look at the 2-issue register remaining pipeline that we had before, right? If I had an exception occurs here, then if you look at this outer order pipeline, right, instruction 4, it's already done. It's already changed, right? And your exception handler potentially needs the X10 value because I want to know where in a PC, where in a memory generates the page fault. Right, so it turns out that your exception handler won't be able to get the right value, and even though my exception handler get the right value, how can I revert the following instruction sequence back? That's an issue, right? So definitely this kind of outer order execution pipeline won't work, right? So we have the idea of speculative execution right now in a way that, well, because we know the PC could potentially change anytime during execution. So any instruction, if it's executed before a priori instruction finishes, is considered as speculative execution. It means that we are not 100% for sure the current execution result is trustworthy for this instruction, or even if the instruction should be executed or not, because a priori instruction could potentially fail. And it would fail in any of the situation we mentioned, like any exception, any page fault, any divided by 0, any overflow. And this situation, they would occur anytime before that instruction, priori instruction is written back. So in fact, if an instruction not yet reaching its write back stage, any later instruction of that instruction cannot be convinced to be executed for sure. So, or at least as what it is right now. So these are called speculative execution. And because it's speculative, so we need to find a way to preserve the capability of restoring its states before it's executed. So for example, if we figure out this is not an instruction that we want to execute, we must be able to flush it. If it finishes, we have to be able to restore the updated register values, and then we need to have the capability of fetch the right instructions at the end. So that's what we need to support speculative execution. And turns out in a pipeline that we just introduced to you, an additional architectural component that we need to add is called ROB, ReorderBuffer. So the reorder buffer is nothing too different, but it's nothing too special, but a buffer to keep track of the program order of instructions. And in most of our implementation right now is combined with your instruction queue by making the instruction queue a circular queue. And then only return an instruction until everyone before the current entry finishes. And so instead of having a write back stage, we right now change the write back stage as a commit stage. So the commit stage not only present the outcome of your execution to the architectural register, but also check if the outcome of an instruction to be realized. So by realize, we mean that an instruction can only finish its execution in a pipeline if all its previous instructions are committed. And if any priori instruction failed to commit it, the instruction will should yield its ROB entry, restore its architectural change. So in other words, if an instruction failed to commit, saying that an exception occurs or branch mispredicted, every entries after the circular queue of your reorder buffer should be cleared, and all the architectural physical registers that has been occupied or changed by those instructions should be cleared. So that's the basic idea of reorder buffer and commit stage. So now the revised superscalar pipeline has a reorder buffer and commit stage at the end. But again, we still have the multiple fetch, multiple issue pipeline feature. So what will happen right now here is that, remember, our instruction queue is right now a circular queue. So I have a head, I have a tail. So assuming that in the first cycle, I have two instructions. So the first instruction must be the one in the head, and the second instruction must be the one in the tail. So the execution is mainly the same as we iterate through the pipeline. However, what you will see is that at the end of the fourth instruction, instead of having the write back, right now we have the commit stage. So here the write back should all be commit stage. So this is a typo here. Sorry about that. And then as you can see, right, in the past, if we have done the write backs or say broadcast our result, this number 4 instruction should be able to finish and leave the pipeline. But right now, because instruction 1, 2, 3, they are not finished yet, so this instruction has to be queued in a pipeline until until all the instruction before it has to be before it committed. So you will see that, well, this instruction can only be finished together with the third instructions, and all other instructions, they will have to stay in a pipeline until this critical store instruction finishes. So in this way, if there is a page fault occurs here, right, we still have the information for instruction 4, 5, 6, so and 7. So we will be able to revert their stages because we still know which architectural registers they will change, which physical registers they are occupying, and who they are. So that's why you need a reorder. The reorder buffer can help to address the case that in case some of them change the PC. And if it turns out that the branch instruction here, we have a misprediction, and because well, so this is probably not an issue, right? But in case the branch mispredicted, because all the instructions follow this instruction, even if they are executing out of orderly, then we still have their information in the reorder buffer, so we are still able to reorder them. So as you can see, with reorder buffer, the instruction fetch, decode, and issue stage, they are not too different. The only thing that you will notice is that each instruction will postpone their departure from the pipeline until instructions before it has completed. So that's the concept of reorder buffer. And similarly, for instructions 9 and 10, previously we will be able to finish right away here, but now you have to wait until the end of the store instruction. So that's a whole story about reorder buffer. So now, a question that I want to ask you. And this question, I have a little bit, I changed the criteria a little bit, is that, well, our pipeline right now, we have you assume that we have a universal pipeline, that the pipeline can deal with everything. But the new limitation here is that you can only issue 2 instructions at the same time. So, if it's a memory instruction, it takes 3 cycles. And for other instruction, it takes 2 cycles. So if that's the case, how good is the following code in with superscalar, autoorder, and reorder buffer? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at the answer right now. Looks like, well, we really need some discussions. Popular answers are between C and E, so a C, D, E. So just go ahead and discuss, express your thoughts. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's take a look at what's after discussion. So after discussion, as you can see now, more of you are convinced that D is the right answer. So I want to invite a group to share your experience of discussing with your friends and why that changed your mind. Okay, Rocket. Who is the scriber of the day? Who is the scriber of the day? Should I have a balloon for you guys to show up? Come on. Okay, Jonathan.
Sorry, I couldn't figure out Zoom. Yeah, so our group didn't quite understand. We decided on 9, but we really don't know what's going on here.
Okay, so tell me about this. Like for this kind of question, if I have this for in a final for you, right? What's the like? What picture or what kind of stuff do you have in mind that you have to draw to solve this one? Like, what's the methodology that you should have to solve this one?
I assume it's like the last question our team answered, where it was like the chart where you had the instruction, and then you draw the arrows to show the dependency, like in the
right. So that's called data flow graph, right? So for this sequence of instructions, the first cycle we fetch 2 instructions, right? Are they depending on each other?
Yes, the add depends on the load. Well, no, it's a false dependency.
No, right? So they don't depend on each other, right? So they can be executed in parallel. So the next cycle we fetch 3 and 4. Are they depending on 1 and 2?
No. Well, 3 depends on 1.
And how many cycles to get the result from 1?
1 cycle. If there's branch forward.
1 is a instruction 1 is a load instruction. So how many cycles to get it?
I don't know.
Well, it will take 3 cycles, right? As we mentioned here, it's a memory instruction, right? So it would take 3 cycles, right? Because the first instruction is right. So it takes 3 cycles, this long, right? And for the branch instruction, it depends on 2, right? So it takes 2 1, 2, right? So 2 cycles, well, at least give it 1 cycle to get the result, right? So if you keep drawing it, right, like 5 and 6, right, they all have the they all depend on 2, so they will be available at the same time. But because right now we have the issue with S2, so the instruction 6 has to postpone a little bit, right? But because we have issue slots still, so it's okay, right? But if you keep drawing, you will figure out that, well, the critical path would take a total of 7 cycles to get all instructions issued, right? So you are not too far away from it, but thanks Team Rockets and thanks Jonathan for working through this with me. But if you draw the data flow graph, you will figure out that for this pieces of instruction, well, as I said, right, with ReorderBuffer, as long as the ReorderBuffer is not a bottleneck, if you have sufficient amount of entries and if you have unlimited number of physical registers, then the ReorderBuffer should not be the bottleneck. So the capability of executing your instructions is completely depending on the capability of issuing your instructions. And for this question, it turns out that it takes a total of 7 cycles if you draw the pipeline diagram as, the data flow graph as what I did here. All right, so so now I believe you guys understand the concept of speculative execution, but one thing that I want you to look at this, right? So if we consider that our modern processor pipeline, we have speculative execution, we have we have a lot of features, right? We have branch predictor, we have caches. So look at this this sequence of instructions. How many of the following could be true? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at your answers. Well, a lot of you pick C, so it's definitely, but a lot of you don't agree that is C. So it's definitely a good time that we should discuss with our friends. So right now, let me send out the screenshot real quick, and then you should be able to open it through your group, through your chat, and then go to group discussion now. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, I see a monopoly of answer C right now. So I just want to invite a group to share us your thoughts. Well, Rocket again. Okay, you got a lot of chance with the new random number generator. Okay, so Jonathan, what do you guys think?
So we think it's 2 for two reasons. The cache is going to contain the content of array 2, and the program, we didn't see a reason why it wouldn't. Was our main argument. It's going to be loaded into temp, so it should be in there.
How come it will be loaded in there? Which line of code will it be loaded there?
Line 7, temp and equals to array 2.
Yeah, but if you look at this one, right, it's x smaller than 16, right? And this is 0, and this is 16, right? Right, so it's x smaller than 16, and okay, so you said here sometimes, well, right, and if your x is 16, right, the 16 here will never be executed, right? So how come you can get that value in?
I suppose we can't.
You can't.
Can't.
Okay.
Yeah.
You can't. Okay. Then what's the other answer?
The program will raise an exception because it goes out of bounds.
Okay. Okay. So other thoughts, other teams. So that's the response from Rocket team. Other teams, do you have any thoughts about this? Other teams? Open to public, any other team? Like any other team, you have different options than 2 and 4. Should you raise your hand? Tell us what you guys think. Okay, Daniel, that's Valor.
Yeah, I think that you could still end up with that array 2 or array 2 at array 116 in cache because of locality, and it's going to bring the entire block in. And since they're only 8-bit integers, or 8-bit.
No, it's actually uint.
Uint 8.
Oh,
so
yeah, it's 8-bit.
Yeah.
Right.
So since they're only 8 bits wide, I think that the cache may contain array 2 at array 116.
But this one is far away, right? So for 15 is 16, and for 16 is 260, right? So what you actually want is 260 times 512, right?
Yeah. Oh, I guess not. I was looking at I indexed it backwards, not. Anyways, forget about that. I went from 1 to 16 instead of from 0 to 16.
Yep. Okay. Other teams. Yep. Other teams, other thoughts. How about mistakes and instincts? What do you guys think? I want to hear about you. Mistakes, you guys are so quiet today. Okay, so looks like nobody wants to talk about this. So let me tell you about this, right? So first of all, if you look at this code, right? So it's the full function will call bar many times. And most of the time, you will see that the random number, because we modded by 17. So most of the time, it's smaller than array size. So the branch, we say taken if the following statement is not going to be executed. So most of the time, we are actually going to execute the statement, right? So the branch will most of the time predict not taken for branch A, because we are having only like 1/16 chances that we should predict taken. So a good enough branch predictor should predict this to be taken most of the time. And then the cache contain this content. So if you predict taken, right? So here's the issue. Remember, we have speculative execution. And if we predict taken, then we are potentially speculatively execute this line of code. And when we execute this line of code, we are going to load the content of array 116, because array 116 is within the boundary. And there's no exceptions should be raised when we access array 116. And then we will use the value of array 116 times 512 to get 260 times 512 in the array 2, which is out of boundary. And then, but the cache would just load the content in without checking the memory, because we are just like, speculatively executed. And we are just fetching the address. And now as long as you have a translation for it, there shouldn't be any problem, right? And as long as that's a valid address, right? So the cache may contain the content of array 2. It may be in a cache. However, because it turns out that this branch is mispredicted, so we will not assign 10 to that value. So what the processor would do is that we load this value, and because we have the prefetcher, we have the prefetching, so we will load value into the cache because it's okay to prefetch. But it's not okay to assign the value to 10 because we know this is speculative execution. And because this is speculative execution, so this under table operations done by your processor, they won't be caught by your operating system to raise an exception. So the answer is that, yes, you guys are right. There are 2, but the 2 are actually 1 and 2. And I also put 4 as an answer, potential answer, because some of you might argue in the very beginning we may have page fault, and so that's an exception. So I accept if you have an answer as D as well. But what would happen here is that, okay, the cache would have the value of this, which is out of bound, because the array 2 only have 256, right? But which is out of bound. But that's something illegal. However, it won't be captured by your operating system because that instruction is under speculative execution. And because it's speculative execution, so it won't trigger the exception handler and because it and also this may be captured by the prefetcher instead of a regular store instruction, so it won't cause any issues at all, right? And the processor would just flush it without letting the operating system know. So that's the issue called Spectre and Meltdown, which was pretty famous in the past. That because we have misspeculation. So sometimes, right, if we have speculation and we find out what's wrong, we would just we would just roll back those instructions. However, memory. What really happens is that because we have prefetching, because we thought it's okay to get more stuff into our cache, so those content that's supposed to be illegally accessed will potentially be pulled into cache. So if you are smart enough, you know how to use examples like the previous pieces of a code, then you can potentially cache as many stuff that you are not supposed to be accessing into the processor. So that's the security bug that people were talking about in modern processors. And however, I won't say it's a bug, I will say it's a feature, because it's just because we have speculative execution. And because we want the instruction to be executed speculatively to give us better performance. And as you can see, the only way you can prevent this happening is that, well, you just don't have speculative execution for your memory instructions. And that would hurt your performance a lot. Winston, question?
I'm a little bit confused on how how you would exploit that by grabbing like memory that you're not supposed to access using that code. Because aren't you limited to accessing your section of the code, even if it is speculative? Like it's like kind of like the virtual memory thing, right? Isn't it kind of stopping you from accessing code that you're not supposed to?
So you are asking a very good question. So some of you are saying about like, okay, if you can modify the operating system kernel, right, then you can potentially exploit that feature. But what you are saying is right. So this Spectre and Meltdown, it turns out that I feel like it's somewhat like it's not that a big issue. So in a way that so far there's no really a user program software can utilize that feature to exploit to get those illegal memory addresses. However, as some of you were saying about like, if you are capable of modifying the operating system kernel, saying that if I have a careless user who'd always, like whenever I install an app, I always click yes, no matter what you want us to do, right? Then you can potentially give illegal software some kind of kernel privilege to have it access these illegal memory addresses. However, in a way, if you have a vigilant user, vigilant enough user, it shouldn't be an issue, right? So that's why we didn't put too much effort on the hardware side to fix that, because we all treat this as a feature, and no matter what you guys said, we are not going to take the speculative execution out, because without that, your processor will not be able to use. And it's more about like the software programmer, you have to design your operating system in a more secure way to avoid people easily exploit that feature. So that's the Spectre and Meltdown. So I just want to give you, and I know there are tons of stuff we can talk about this on this topic, but I just want to let you guys know that if you ever heard about this and where it comes from is because we have speculative execution. And speculative execution could potentially bring things that you are not allowed to access, but because the operating system has the check of your permission of accessing. So right now, it's not possible. Well, I won't say it's 100% possible, but right now, nobody ever use that feature to exploit anything from your system. So your system is still safe until some of you might discover the way to exploit it. But right now, we are still safe, even though you have an old processor. So that's what I want to say. And now, but just give you just keep in mind how important is it to notice that sometimes those new hardware features, they could potentially cause issues in software, and Spectre and Meltdown is an issue because of speculative execution. All right, so talking about speculative execution, so we have this dynamic sequence of instructions, and you remember this question, and if you remember this pieces of a code, that it takes about 7 cycles to issue all instructions, and we can 7 cycles to issue the whole instruction. The average CPI of this pieces of a code is actually pretty low. So for this pieces of instruction, you will see that, well, the average CPI that we can achieve is about is only about 0.75 because we spend 3 cycles for every 4 instructions. So one thing that I want you to know is that, well, we write a lot of this type of code, and we have a lot of wasted issue slots in our program. So if you look at the instruction level parallelism, which means the capability of instruction issuing instructions in the sense at the same cycle is very low, because in a lot of cases we tend to write code with a lot of data dependencies. So now I'm going to introduce a new concept that has been common in microarchitecture to incorporated in microarchitecture called simultaneous multi-threading. And you already met one of the inventor of simultaneous multi-threading. That's Joe Emmer. He have just gave a talk with us a few weeks ago. And another inventor is Dean Townsend. He is my advisor, so you can see this is me. And you can get an idea how tall Dean Townsend is. And and he is also the co-inventor of simultaneous multi-threading. And I feel like I'm fortunate enough to work with them. So but what's simultaneous multi-threading? So it's the basic idea of simultaneous multi-threading is that because the instruction level parallelism of a single thread is really low. However, we have more functional units than the instruction level parallelism that is available for all programs. So what if we try to exploit thread level parallelism, meaning that we are able to schedule instruction from different threads, processes or programs to execute in the same superscalar pipeline. So the basic idea is that the microprocessor itself is still a single processor. However, it presents an illusion for multi-processors for the operating systems. So the basic idea of simultaneous multi-threading is that, okay, so the left-hand side is our old friend, the linked list, right? So if the linked list cannot fully utilize the hardware like this, right? Then what if I have fetched instructions from another thread like this? And in the meantime, if I figure out that, well, I have free issue slots to use, I just schedule those instructions in my pipeline. Right, so as long as I have free issue slots, I can put those instructions from the other threads or say the other process in my processor pipeline. So in a way that, well, it still spend the same amount of time, or maybe to execute this linked list code. However, in the meantime, I use my free issue slots to make progress for the other threads. So my processor is fully utilized, and it's just a single processor, but I can do more things in the meantime. So that's the basic idea of simultaneous multi-threading. So now I have a question for you, is that if I want to make my superscalar processor supporting the idea of simultaneous multi-threading, what are the functional units or what are the architectural components that I need to duplicate? All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looks like we really need a group discussion now because there are ties in B and C. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now after the discussion, it seems like, well, interesting, right? So look at after discussion now, B is the most popular answer. So a lot of you think 3 is the right answer. So let's pick a team. Okay, Rocket, how come it's so popular? You guys are so popular today, right? So Rocket team, what do you guys think? Okay, Jonathan.
Okay, so our team thought it was 3.
Okay, what are the 3?
Program counter, register mapping tables, and the reorder buffer instruction queue, because these are needed to run threads concurrently. Everything else would be nice to have, and it would improve performance, but it's not needed for the illusion of multiple threads.
Okay, perfect, right? So we need 3 of them. Okay, so Rocket team score 1 finally, woohoo, for today, right? So we need a separate program counter because we need to keep progress of different processes, different threads. We need a different register mapping tables because we want to know, like for each instructions in each program, what do we like where are their architectural registers mapped to. However, you can still share the physical registers. You can share the LU, and sharing the LU is actually the whole purpose of simultaneous multi-threading, right? So if you look at this one, right, you need all you need is that we need 3 things to be duplicated to present an illusion of multi-core processor, right? So actually, if you want to support simultaneous multi-threading, right, all you need is that I need a separate PC, I need a separate register mapping table, and I potentially need I need to have 2 instruction queues to support simultaneous multi-threading. Then I'm done, right? So now I just want you to think about, like, okay, what's the benefit of having simultaneous multi-threading? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question right now, looks like C is a popular answer. So let's have a quick group discussion and see what you guys think after the discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let me pick a team. Oh, Rocky team. Okay, let's try another team. You guys have too many chances today. Okay, Mystics. So, okay, so it's also interesting, right? After discussion, you see C and D's, they are popular answers. So, Mystics, who is your scriber of the day? I miss you guys. Okay, so Joshua.
Hi, Professor.
Yes.
So we believe it was C2.
Uh-huh. Okay,
And
what are the
one,
two?
So I believe the first one is correct. Is that it makes it
How
more,
come?
because essentially when I do hit a misprediction and normally I would stall, I can kind of context switch and work on.
Or say you don't have to context switch, you just have schedule instructions from the others, right? So instead of stalling, or say potentially you will fetch a lot of instructions that are incorrect, you just fetch those instructions that you know for sure, right?
Correct. And then we, I think what we decided was we thought 3 was also correct.
How come? Because
I think
similar situation.
for the same kind of reason, right? It's like essentially when you have any kind of stall happening, you can switch over and do other work because you have two.
Okay, why don't you agree with the second?
So the second one is it's not going to improve the throughput of a single threaded application because it'll only be executing on one thread, right? So there's no way it can use that secondary, or SMT goes anywhere from 2 to 4. There's no way it can actually use those execution units.
And the other thing is that, right, it can potentially hurt, right, because you are sharing your resource with others, right?
Yeah.
And the third one, as you said, you can execute from other threads. Now goes to the fourth one.
The fourth one, SMT processors can have higher cache miss rates. I didn't think this was true, but this was just kind of intuitive for me. I didn't have a great reason for it. It just intuitively didn't seem correct.
So think about this, right? SMT, you share the cache with others as well. So in this way, is it higher or lower?
If we're sharing the cache, you could have higher hit rates if you're using the same data in a read-only fashion, right?
Yeah, but if it's a different process, right? Mostly, it could hurt.
Yeah.
The cache miss rate, right?
Yeah,
so
that makes sense.
Yeah, so the answer of this question is actually I will put 3 here because in general, because you are sharing, right? So your hit rate is worse, right? Meaning that your cache miss rate is higher.
Yeah.
All right. Thanks for your insights. And Vincent, okay, question.
Yeah, I have a question. So we're kind of talking about number 4 about having a higher cache miss rate due to us sharing the cache and the threads. Would this kind of also be kind of dependent on how the programmer uses those threads as well?
Yeah, so the same set of applications, if you have the same application competing with each other, right? And if they are running together, and if they are both in different processes, right? It's unlikely that you are going to improve their cache hit rate, right? So you read a paper of helper threads, right? And the helper thread is actually, they tweak the application in a way that is not a same application, it's a supplementary thread that does prefetching, right? But if you don't do anything to your original program, it's very likely you are going to compete with each other. And because in the operating system, even though they are the same program, they access the same data, but because they are in different process abstractions, so they turns out to be different memory addresses, they cannot be shared. Okay. All right. So before you leave the classroom, and so sorry for taking more time than expected. So before you leave the classroom, there are a few things that I want you to notice. First of all, project due next Monday, reading quiz due this Wednesday, assignment 5 will be up tomorrow, start early. And two things that are probably excited to you, and I want to let you know. First of all, the class evaluation called iEval will starting tomorrow until December 11th. And if you do enjoy the class, I do encourage you to fill out the survey to let us know your opinion and let us go know that how good we are doing. And the most important thing is that don't forget to take a screenshot of your submission and submit it. The screenshot through iLearn, it will count as a full credit assignment. And to encourage you doing that, I will, and if you don't want to fill in a survey, that's okay. I will drop your lowest 2 assignment grades anyway, although that lowest 2 would include this iEval one. So if you submit this one, it will be a 0 credit. If you don't submit it, it will be 0, but it will be automatic drop. So you don't have to feel obligated to submit iEval if you don't feel comfortable to. But if you do, it will count as a full credit assignment, and we will drop your lowest 2 assignment grades. So if you didn't do well in 2 of your homework assignments, then or you decided not to turn in assignment 5, you should definitely try to do your iEval. And the final exam, it will start from December the 10th to December the 15th until the end of the day. However, some of you tend to give us trouble in the last minute. So this time I want to say, if you started after 12 p.m. December 15th, sorry, we cannot provide you any technical support because it's just not giving us sufficient amount of a time to address your issue. So if you really if you are really uncertain about your network connection, you should pick an early enough time to start your exam, so that at least if something happening, we can find a way to address you. And it will be a similar format as midterm. You have to find a consecutive 3 hours you pick, and you will be given like twice more time, and it's going to be 1.5 times longer. And again, we will give you a sample final at the end of the last lecture. So because we are running out of time, I will release more detail in the next lecture. But other than that, enjoy the rest of your day. I still have office hour to 9. So if you have any other question, feel free to use the office hour link. I will be there. Other than that, enjoy the rest of your day.